Identities is an extremely important part of someone's life. Especially, everyone wants to know their identity, whether it's from culture or from your own personal identities, who you are as a person. We spend our lives looking for that. And as long with this, in math, there are identities as well, trigonomic identities. Today, we are going to learn about trig identities and equations. Come on! Using what we know about the right triangle, we know that the opposite is that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is the opposite over adjacent. Using this, we can help prove one of the trig identities in your formula booklet. So using what we know, that sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, we can figure out, if we put this into an equation of sine of theta over cosine of theta is equal to tangent of theta. To prove this, let's put the SOHCAHTOA into this. Well, let's replace sine and cosine with opposite over hypotenuse and adjacent over hypotenuse. Due to this, the two hypotenuse will cancel out, leaving us opposite over adjacent, which is tangent of theta. Along with this, trigonomic identities can also be found in the Pythagorean theorem of a squared plus b squared equals c squared. And in the right triangle, we can find that the opposite a squared, c squared, and b squared. Using this, a cool trick you can do is that by dividing c squared by itself, we end up with 1 over here, and we end up with a over c and b over c here. And we squared them. And what do you notice about this? B over c and a over c. A over c and b over c. That's right. They are both the same. They are SOHCAHTOA. We can now state that we can now replace AC over BC with our trigonomic identity of sine of square root of x is equal to sine square root of x is equal to cosine square root of x, which is then equal to 1. So knowing that, we can now so using that, we were able to find one of the trigonomic identities in our formula booklet, just from the right triangle. From there, we can find 2 more trigonomic identities in your formula that aren't in your formula booklet, but will be useful to know when we're solving trigonomic equations. So, knowing that sine of x squared, sine squared of x plus cosine squared of x equals 1. Another one of our trigonomic identities is that sine squared of x is equal to 1 minus cosine squared of x. And using by subtracting 1 cosine squared of x to this side, we end up with sine squared of x is equal to 1 minus cosine squared of x. And we can do this as well with cosine squared of x. By keeping cosine squared of x, instead subtracting sine squared of x to that side, we end up with cosine squared of x, which is equal to 1 minus sine squared of x, which looks a lot like this. So now that we understand our trigonometric identities, so using just the simple Pythagorean theorem and the key and SOHCAHTOA, we were able to find 4 key parts of the trigonometric identities. So knowing this, you might be wondering, why are we learning trigonometric identities and equations? Well, even though you won't be using complex trigonometric identities and equations in your life, you will still be using trigonometric identities in your life. Such as if you go into the work as an architect. In architecture, trigonometric identities are seen often in cars, chairs, and usually seen in large infrastructure. They're usually used to measure sides that are unstable as well. Music theory, trigonometric equations are used to find the frequency of the instruments being played on a violin. Such as a violin, it acts as a sine. But for engineering, trigonometric identities are seen in mechanical and are seen in many popular types of engineering: mechanical, electrical, and many others. This is our IB example. Just by looking at this equation, we can tell that there's already a double angle formula in it, sine 2 of x, which in your trusty handy formula booklet is 2 sine of x cosine of x, which we can replace the sine 2 of x in here in the equation. So we have 2 sine of x cosine of x, which is equal to 3 cosine of x. So now we can multiply the 2 by the 2 sine cosine of x to get 4 sine of x cosine of x, which is equal to 3 cosine of x. So at this point you might be wondering, what should we do? Well, see how on this side we have 3 cosine of x, and this side we have 4 sine cosine of x. We can immediately tell that I can tell that by subtracting the 3 cosine of x, we can then factor out that cosine of x. So by subtracting 3 cosine of x, we're left with 4 cosine of x, 4 sine of x cosine of x, minus 3 cosine of x, which is equal to 0. So factoring out the cosine of x, we're left with 4 sine of x cosine of x, 4 sine of x, minus 3, which is equal to 0. So cosine of x equals to 0 is simple. And since our interval is between 0 and pi, on the unit circle, that means that anything under this we do not need, since pi starts here and 0 starts here. So the only time cosine of x, which cosine of x is x in the unit circle, would be, it's the x in the unit circle, would be here at pi over 2. At pi over 2. So since we can't get any other more points here, that will mean the first term and the only term for cosine of x in this interval is 0. Is pi over 2. Now for the other one, it gets a bit tricky because it's not on the unit circle, as you will see after I do some basic algebra to find it. So the equation we got from after factoring it out, we got 4 sine of x minus 3 equals 0. So by adding 3, we then get 3 4 sine of x equals 3. And then by dividing that 4, we're now left with sine of x equals 3/4. Now this is problematic because it isn't on the unit circle. But since it isn't on the unit circle, we can go and use our trusty TI-84s, which one day they're going to rule the world, trust me. But using sine of x equals 3/4. But for this, I will be using decimals. So we can say x2 is equal to 0.848 and 2.294. And that will be your answer for this equation. My next IB example is going to be this. It's going to be asking for part A. It's asking for us to write an expression for cosine 2 of x plus sine of x in terms of sine of x only. For B, it's asking us to solve the equation cosine 2 of x plus sine of x equals 0 for the interval 0x. To start, let's face A, which is a lot more simple than you think. So since it's only asking for us to solve for an expression, we don't need to find an answer for part A. We only need to write an expression and into terms of sine of x only. Well, up here we can tell that cosine 2 of x is in our double angle formula, and cosine 2 of x has 3 ways we can do it. We can have cosine squared of x minus sine squared of x, or we can have 2 cosine squared of x minus 1, or 1 minus 2 sine squared of x. Since it's asking for sine of x only, I can recognize that we should turn this into 1 minus sine of squared x plus sine of x, and thus we have our expression for part A. For part B, it gets a little complicated, this time it's asking us to solve for an equation for the interval 0 to 2 pi. So this time it's asking us for cosine squared of x plus sine squared of x, sine of x equals 0. And just like in part A, part B, we're going to have to transform this cosine to the double angle formula of cosine 2 of x into one of its double angles. And let's try to turn this into, once again, a quadratic. So 1 minus 2 sine squared of x. With this quadratic up, we can have 2 sine squared of x plus sine of x minus 1. From there, which is, what to do? We have a quadratic! Oh my gosh, that's hot. But yeah, with a quadratic, we can now find the 2 terms that we're looking for by multiplying 2 sine squared of x by 1. We get negative 2 sine. No, wait, it's a positive. Sorry, it's a mistake. But yeah, since it's a positive, but this is a negative, we end up with negative 2 sine squared of x, which is equal to something that equals sine of x. And since we're looking for what sine of x is, the answer would be 2 sine of x minus sine of x. So then we would import this into the equation once again. So now we would have negative 2 sine squared of x plus 2 sine of x minus sine of x plus 1 equals 0. From there we can cut these 2 off. And now by taking out a negative 2 sine of x, negative 2, let's erase this so we have more space to work. Negative 2 sine of x sine squared of x, we're left with 2 sine of x plus 1. No, yeah. Now we're left with sine of x plus 1 with minus. Let's also take out negative 1 from here, so then it's sine of x plus 1 equals 0. And that's only take 2 sine of x, so instead we have negative 2 sine squared, and take this. So now we have 2 of the same. So now we can find this with the power 0 using quadratics. So now we have 2 sine of x plus 1 equals 0, and negative sine of x plus 1 equals 0. Let's use a different marker. Actually, let's use a different marker for this one, just to make this stylish. Now we have 2 sine of x. Oops, wrong one. Negative sine of x plus 1. And so for these two equations now, we can now solve for it. So let's first start with this, which I'll be calling x1. So for this one, we're using basic algebra. For now, we can just use basic algebra to solve for it. Minus 1, and then divide by 2, we end up with sine of x. We end up with sine of x equals negative 1/2. And we also end up with 1 sine of x equals 1. Sine of x equals 1. So now that we know that this, we can now look, since we know that all quadratic, and these are both on the unit circle. So now we can solve for both of them. And we have to solve in between the interval one full turn, one full circle. So sine of x, sine of negative 1/2 of x can be found here and here. Negative 1/2. Since it would be square root of 3 over 2 negative 1 over 2 negative. Same thing over here. Square. Oh no, it would be positive, this would be all negatives. So yeah. So knowing this is asking us to find in the interval of one full rotation. So knowing that this is 2 pi, and seeing how that sine of x equals negative 1/2, to figure this out, I'll start counting by 6. This is 3 pi over 6. And then this is 6 pi over 6. So since this is right here, I'd say that it'd be 7 pi over 6. So the first x1 would be 7 pi over 6. And then from there, this is 9 pi over 6. This is right before the 12 pi over 6. So the next term it will fit would be 12 pi, would be 11 pi over 6. So that's for sine of x equal negative 1/2. But for sine of x equals 1, a positive 1, it will only be found up here where pi over 2, because 1 is, sine of x is only ever equal to 1 at pi over 2. So your final answer, you have 7 pi, x1 equals 7 pi over 6, 11 pi over 6, and x2 equals pi over 2.